get started with our recording. As you saw, as we started here, we're in the middle of week 9, and another document that is now available for you to take a look at is for our project proposals and the projects for this course. I'll spend more time on it next week, so I don't want to belabor the details today. We have time. We're not in an extreme rush for it, but I'm just mentioning that it is available. You can click on the link for project proposals, and you'll basically just get a version of this document popping up. For now, I would say your only action item is between now and, let's say, next Wednesday, when more of us will be assembled here again, just to take a brief look at it. That's all I'm asking of you, and then we will spend 10 plus minutes, as much as it takes, in class next week talking about the details, and then you will still have plenty of time beyond that to actually do what is necessary for the project proposal stage of the projects that we have here. So for now, you can click on that link in Canvas, take a review, a quick review, just read through it of what the projects are about, and then when we discuss next Wednesday, hopefully you'll have questions based on what you read, and we can go into the nitty-gritty details at that point. So long story short, that is coming. Be aware of it. We don't have to do too much with regards to it right now. Because there's still some more things I really want us to make sure we cover. 2 more critical topics, I guess, that I'd like us to cover before you really start in earnest on those projects. I mean, we have a lot. We have a lot ready to go with regards to what you've learned already in C. There's just, much like our topic on functions, there's just a couple other things that'll make your code a little bit more tractable in terms of trying to solve the problems that you'll have to solve to implement something fun for those projects. So this next topic is labeled structs, and some of you have already started on lab number 7. Lab number 7 does make use of structs. It also kind of combines a lot of the other things we've been learning so far this semester. Structures are important because data generally just has structure. And we've been doing okay, getting reasonably far so far this semester by just assuming for the most part that data just maps and can be represented with one of those individual built-in types in C, your ints and your floats. And we've been okay with that. We have an array of ints to represent this, an array of floats to represent that. But data tends to have multiple aspects to it. Most data sources have multiple aspects to it. If we wanted to consider, just as a kind of academic example, we were going to write a C program that manipulates our Canvas gradebook, that has entries in it corresponding to the students in the class and their last names, and then entries corresponding to students and their first name, the section number, if we had A, B, and C sections, scores for various quizzes, perhaps those are integers, lab values, perhaps those are floating point values. If I were to tell you to implement that today or to build something based on that premise today, you would be able to do it. There's nothing new in terms of conceptually there, in that you could consider making 7 different arrays to store that information. For all the students in my class, I'm going to define a series of arrays. One array, which would ultimately be kind of a 2-dimensional array, right, to store all the first names, call it first. One array to store all the last names, call it last. An array perhaps just of characters to store the section character, etc. Separate arrays for each of those particular columns that may go into a gradebook for a course. Then consequently, you would have to kind of just manually keep track of the index, right? And each index into all of those arrays would correspond to an individual student. So you would have student Alan here in the class. He would be index 0. And so you'd have the first array. Index 0 would correspond to Alan's name, his first name. Index 0 of the last array would correspond to the last name. And so on for each of the individual entries in each of those kind of separate arrays. That approach would work, so it's not wrong at all. But it definitely gets kind of unwieldy. And certainly as you decide, well, actually 2 quizzes is not enough, we need a 3rd quiz, and we need 3 labs, or maybe potentially an arbitrary number of those things we want to compose together, it starts to get pretty unwieldy. You're just having these large number of arrays. If you have functions to work upon those arrays, you're going to have all of those arrays be inputs to the function. You could get it to work. It's not like we can't do that, but it just starts to become a little unwieldy as the gradebook would start to expand. We could also, as an alternate approach to consider, just have one big kind of data blob 2-dimensional array, where instead of worrying about type-specific context, you just recognize that we have a series of rows, we have a series of columns, it's ultimately just bytes. we have this just big blob two-dimensional array that we're just going to kind of access things from there. That's not so dissimilar from how the underpinnings of an actual database would work under the hood. But in terms of writing a C program to be able to access that, that starts to get really complicated because of the types issue. If all of our types were single byte types, that would actually work. But they're different, right? The first name has a certain length of cars, last name has a certain length. These are individual bytes, these are integers, those are floats. Keeping track of all of that is an implementation approach. We could probably work it out. That code would be pretty filthy to kind of look at there and work with. So we have this concept of a struct in most, if not all, programming languages, including for C. It is short for just structure or structured data. It is a way of just grouping different variables into a single type. So for this example, where we have the students in a grade book, we could then create a structured type that we would want to call something like student type. And as part of that structured type that we are creating, we would then have entries within that structured type corresponding to all the stuff we need to represent an individual student. We'll talk about syntactically how this works, but conceptually that's all a structure is. That if we know that a student could be composed of a first name and a last name and a section and quiz and lab scores, we would declare a new type in our program that would store exactly that. And we call it something like student type. And then when it became time to now write a program that implemented a grade book in which we have multiple students, we would then in our program declare an array called students or something of that particular type. And then otherwise, there's a little bit of syntax for accessing the individual elements inside that structure. Otherwise, all the stuff we've already been doing with having arrays, having an index into the array, using for loops to work our way through an array, all that stuff is exactly the same as what it is before. The main difference now is we can think about the data our program requires in a little bit more sophisticated of a fashion because we don't have to worry about is an int or a float. Do we need an int or do we need a float for this particular data? Now, as part of that problem-solving process, the answer is, well, maybe we need both. And maybe we need multiple of both for our variables we're interested in. So as part of our problem-solving process, we may say, is there some structure to the data we're working with? Do we need to declare? Do we need to create such a structure? And oftentimes, once you've done that and have thought that through, and it's kind of multi-layered version of the same problem we've already been solving is, okay, before we had to worry about what is my data type, what should I call my variables, and now it's kind of multiple of that. It's what are my data types, what should I call my elements in a structure, and then I still have to name the variable at the end of the day as well. But once we have that in place, then in theory our code should be a lot cleaner, a lot easier to kind of work with, a lot easier to expand as well. And there's really just the three steps. We have to first define that structure type. We'll have to give the type a name like student type. We have to give a name and have a type for each of the individual elements, the data members or structured components. I'll use this term kind of interchangeably during this topic. We then have to create one or multiple struct variables of that type. So with ints, they're kind of built in. With floats, they're kind of assumed we have them. For this, we first have to define what that type is, then we create variables of that type. And then there's a particular operator we use to access the individual data members within a variable of that particular type. So our syntax is going to start to look a little bit more convoluted than what it was before, but that's all we're ultimately doing. Think of the student example when you're thinking about structs. I just have these components or these data members. I'm going to use a dot operator to access each of the individual members. And then what I get back is whatever that particular variable type was. If it's an int, I do int stuff with it. If it was an array of cars, I do array of car or string stuff with it. We get to the individual member, and then we can treat it like any other variable. So once we've defined our structure and get it set up, the rest of the code doesn't add too much complexity for us here. Here's the basic syntax. The keyword is called struct. Struct and then the name of the structure, and then curly braces, and then whatever those individual elements are going to be or our members are going to be inside our particular structure. That's the structure tag. Technically, we don't need to have a tag here, but this is usually good practice to say struct name of the structure. We then have all the data members, whatever they're required for the particular problem that has some structure associated with the data for it. And then there's a semicolon at the end. And if you miss that semicolon at the end, you'll get a weird looking compiler error. And there'll be one of those compiler errors where the error will be on the next line of code, but it is ultimately expecting a semicolon there. So unlike our if statements and for loops, when we have our semicolons there, we don't have a semicolon at the end. When we have our curly braces for for loops and if statements, we do not have a semicolon at the end. We declare our structure, there's a semicolon at the end of it. That has defined a new type, but has not yet allocated any memory or defined any variables of that type as of yet. And there's actually a couple different ways you can do that. At the time you define your structure, you can actually choose to define a few variables of that type at that time. You can say, here's my structure, and then here's 3 variables of that type. That's more of a textbook example because it's not as common. I think more oftentimes we'll want to declare our structure somewhere in our code, probably in a header file, right? It's one of the things that defines the structure of our program. And then the ever-present ellipses here, ... Somewhere later on in my program, I'm saying I have a few variables of that particular structured data type.
Are those variables local within the structure, or are they global?
These would have whatever scope in which this block of code was defined. So if you did it before any of your functions, they'd have global scope. If you did it within a function, they'd have local function scope. That is also kind of the downside of this particular approach, is the actual definition of that structure is limited to these 3 declarations. You would have trouble writing a function that would make use of it. This approach, where we define a structure early on, it's in our .h file, it's one of the first things in the top of our program, then allows us to do things like write functions that take structures as input, or functions that return structures as the return value. But if nothing else, we can then declare the variables of that type at some later point in our program. You may have seen examples that don't use this struct keyword. Again, we'll talk about in a minute why that can be the case. But otherwise, we say, here's the name of the structure we've defined. Call it whatever you want, but you're the one who has to use it and understand and remember what that structure was supposed to be. We have to then kind of think about, these aren't exactly variables, right? But they're kind of like variables in that the name of them should signify some meaning, right? So we do have to kind of, up front, before we've done any of the real programming with this example, what should the individual types be for the component, the data members of the structure? What should they be named? And then we still have the general variable naming problem of, okay, I now have this structure called student data. I need a few students in my course. What should I call them? Okay, well, student 1, student 2, student 3, whatever you need to call them is what you wind up calling them for your program. And we see here, unlike an int, where it's just int, variable 1, variable 2, variable 3, at least unless we add an additional keyword that kind of eliminates the requirement, we have our structure here. The data type is struct student data. So when we declare a variable of that type, we say struct student data, and those are the variables of that particular type. It's a little extra wordy. We can initialize them somewhat similar to arrays, and then we can actually also initialize by the member name itself. So it's sort of similar to our syntax for initializing arrays in that when we declare a variable of that type, we use the curly brackets again, curly braces here, and then we initialize each of the individual components of that structure. It's a little hard to read in my opinion. This goes to like, when do we have things in a header file? When do we have it just earlier in our program? To me, it's hard to read this line of code without also having this definition handy, like on the same screen or on a second window or something like that. Because in terms of what's happening in that initialization, it is taking the particular types and it's doing an individual type initialization. Again, we have a string or a character array here. We initialize that with double quotes, and the compiler kind of takes care of that for us. We then have an individual character type. We initialize that with single quotes. 2 integers, and then 2 floats. Well, if you get one of those wrong, it's going to be really hard to track down exactly what's happening here. Similarly, if later on you decide, I actually need a 3rd quiz and a 3rd lab, and I need to change my lab section from a letter to a number or something like that. I decide to change the structure of my data. You have to go back and then check every time you've initialized a variable of that type and change it accordingly. The other approach, which takes more typing, but I think is a little bit easier to reason about as you're reading either your code or someone else's code, is to use the member name itself. And we're going to talk about this so-called dot operator to access the individual components, but that's explicitly what it is doing. You are saying here, I have a student, student 2, these are the individual components, and this is how I'm initializing them by name. There's a first name component. We'll say dot first name, that's the first name component, and that's Philip. Last name Jones. He's doing a little bit less good in the class, which sounds about right. We also then do not have to do it in order at that point. I could have done last followed by first, or I could have done lab 2 as initialized first and then the other stuff at some other point. You're just specifying as I'm allocating memory for a variable of this type. Here are the individual members, and in this case, I don't have to even initialize all of them. Here are the individual members, here are their names, and here's what I'd like them individually to be initialized as. Questions about this example so far? Yeah, sure. Declare what again? Right, so what looks a little redundant is, and there is a workaround for this that some people use, is that we declare this data type here, and the syntax is to declare a variable that type is still to say struct and then the name of my structure. So it looks a little redundant because we're using the struct keyword in 2 places. One at the time we're defining the data type, and the other when we're actually creating variables of that data type. So yes, everywhere you would have int a in your program, you would have struct student data in your program, then the name of the variable of that student type. So it's a little extra wordy, at least with that version of it. Well, let's make sure we're all on the same page with regards to that. And the best example I have is kind of a mediocre one, but let's go back to this example here where we have a problem and we've been working with data that has some actual structure to it, conceptual structure to it, meaning we have a grade book or anything that can be put into a spreadsheet or anything that has multiple aspects of the data. It's not just data that's only an integer or data that's only a float or data that's only a set of strings here. It is some data like a student record that has a lot of those different things. You could write a program that doesn't use structs at all and could work with a student grade book. And that's what I was kind of getting at here. You could have an array of names, an array of quiz scores, an array of lab scores. You could do it, and we've been kind of doing that all semester long. This approach of having structured data is going to allow us to first kind of explicitly define the data storage by its component members to have this be kind of a built-in variable that we can then use in our programs. And then we get kind of all the benefits of having a variable of that particular type. We can then, I'm jumping around a little bit here, we can then, after we've declared it, we can define an array of students. And that would need to be the only variable in our program for working with our student gradebook. We can have functions that take students as inputs and functions that generate students as outputs. Our code is going to wind up, I think it's correct to say, it's going to wind up being a lot cleaner to work with when we're thinking about data in terms of the structure and the relationship of the individual components of that structure versus just going back to the base principles of I either have an int or I have a float. I now have something that's both, and it's combining both of those. It's a good question. I do feel like you'll see it pretty quickly. You know, in Lab 7, you'll definitely see it pretty quickly that having the structure is really what allows that code to be feasible at all and tractable at all to kind of work with here. So just like that initialization syntax, and this will be really one of the last syntax things I'm going to talk about here, to access the individual elements or those member components, we use a so-called dot operator. So if I were to declare elsewhere in my code a new student data variable called student3, And I'm not initializing it at declaration time, right? Sometimes we want to do that. Other times we're not ready at the time we declare it to initialize that variable as of yet. When we later on in our code, there's our ellipses again here, decide it is time to initialize or set the value of that structured variable, we get to choose one or choose all of the different components of that structure to then initialize. And we use that dot operator to do so. If quiz1 was just an integer type, we would say quiz1 equals 9. But it's student3.quiz1 we're initializing here. And so we use that dot operator to indicate, here is the variable name we're initializing. It's a structure. We're not initializing, we're setting some component of that structure. In this case, the component named quiz1, we're setting it to 9. That's for initializing. That's also for using. If I choose to now print out the value of the lab 2 score for student 3, again, you probably have to have that structure definition handy, right? In another tab, on another window, because you have to kind of remember or have that context available for, okay, I have lab 2 defined as part of my structure. What was lab 2 again? Because I don't see it here. You don't see it here otherwise. It's in the structure definition that lab 2 is part of that structure, and it happened to be a float. You either have to remember that, or you have to go back, or you're going to get the same kind of compiler or runtime errors we were having like back in week 2 of the semester, right, where I was doing int stuff, but I meant to do float stuff, and vice versa. In this case, now, if I want to print out lab 2, I have to remember that it was a float. That's how we defined it. That's what it just happened to be for this problem. And so when we want to print it out, we treat it like any other variable of that type. We're just grabbing the individual component. So the dot operator then is really only the last new thing about working with structs. You define them. You define the structure of the struct first, the individual components. You declare variables of that type of structure. And then when it comes time to either read or update a value, a subcomponent of that structure, you remember the variable name you're working with, and you then just use the dot operator, with all the caveats that apply, right? And just because it's a structure doesn't get you around all the other shortcomings or headaches of working with C. I want to update the first and last name of the student 3 after the time I've declared it. I can't just say student3.firstname equals Mani. It's tempting, but we can't do that because we couldn't do that for arrays. At time of a declaration of arrays, we could initialize the entire array. And that was what we were doing either here or here. At time of declaration, you can initialize a whole array. But after the time of declaration, we have to use, if it's an array, some code or some function to initialize that value of an array. It's a good use of the string copy function. Update this array with this array. That's the closest thing to student3.firstname equals Mani. In C, at least, you can't do that. You have to then write whatever code or call whatever functions to update your array after the point of declaration here. So with that caveat, which is really the same for any of our arrays, accessing the members of a data structure operate on similarly to any variable of that same type. I have this as an example in Replit, but it's really not anything beyond what's already in that code here. So maybe we put this in a header, maybe we don't. We declare a structure called student data. I use _s as kind of habit, just to kind of imply that it's a structured data type, but you're not required to name it as such. And it has these components associated with it. And this code is just showing the 3 ways you would then initialize a variable, 3 different ways you could initialize a variable that is a structure type. One is kind of that array type syntax for initializing the variable. You're saying there's components, and I'm going in order, and I'm initializing first name, then last name, then lab section, then quiz 1, quiz 2, lab 1, lab 2. And it's using that curly braces, using that array syntax for initialization. What's new now is you can also initialize it, also kind of using the array syntax, but doing it by names of the individual component. The dot first name is going to be Philip. The dot last name is going to be Jones, and all those other components are going to be set as such. And then there's the syntax for, I guess, will probably be the most common case of working with structured variables is Yes, we initialize them at declaration all the time, but then we use them for all sorts of other purposes. So when we use those variables for all sorts of other purposes, we use that component selection operator. I'll just call it the dot operator. And you would say student3.quiz1. That is the quiz1 component of a variable called student3 that is of that type student data. And all the other rules that apply for ints apply for student3.quiz1 because it's an int. Likewise, the reason we have to use string copy here is because all the rules that apply to an array of characters, a C string, apply here because that's what first name is defined here. It's a C string or an array of characters of size 32. But otherwise, when I want to print it out, when I want to update values, when I want to pass them as inputs or do anything with them, the syntax and the usage is exactly the same. Once I get st.lab2, it's a float. Everything, all the rules that apply to floats apply to that element because that's all that it ultimately is. So when I run this and it's going to print out %s's lab2 score was %.1f, what should this print out? So Mani did pretty good on lab number 2. What is... All right, Replit changed like overnight. Okay, results of your code will appear here when you run the project. When did this change? This past weekend. Okay, well, it's fine. The console and the shell were always kind of superfluous, right? We were using them kind of the same way. The shell still gives us our shell. It looks like console gives us the result of running these programs. And then it's kind of nice, I guess. You can see the result of running it multiple times. And as you make changes, it's a little bit easier for tracking changes. That's a relatively recent change that I had not noticed until right. Error or not. It says if it finished or not. It says how long it took to execute and when you ran it. It's better than what it was before. Before it was just another shell. Now it gives you a little bit of feedback. Now if I want to play with the results of the execution, I have to kind of do it manually. But that's fine. That's how it kind of was already. Not into the console window anymore, it appears. We still have the shell. So we can still do everything that applied to either or now applies to the shell window only as of today. We have to be agile with our software that we are using here. So I mentioned this whole kind of superfluous usage of the struct keyword. That is the correct syntax. The other keyword, and we actually briefly used it on Monday, but we did it pretty quickly and I didn't want to focus on it yet, is the use of the typedef keyword, which allows us to give an existing type just a new name. So this is perfectly valid syntax in C to say, for an existing type, define it to be named something else. And there's all sorts of reasons just for code readability you may want to do it. Sometimes it doesn't actually lead to improved code readability, but it's more of the opinion of the developer that I don't want to work with unsigned car types. I want to call it a byte because I know an unsigned car is a single byte. And when I'm writing my code the rest of the time in this program, I want to be able to call things bytes versus calling them unsigned car. But that's all the typedef keyword is doing. It's kind of similar to the #define keyword, which is kind of replacing one token with another. That's all pre-processor macro stuff, whereas typedef is actually supported as part of the compiler itself. So in theory, it should lead to better either compiler errors or warnings or better syntax highlighting and things like that. So there's some benefits of doing that. We have not been using it for the most part this semester. The most common use case for it, beyond just, again, defining your own types using different names for them, is to get rid of the kind of have a less wordy version of the struct declaration. At the time I'm declaring my structure, I can wrap the whole declaration in a typedef command. I'm saying typedef the following, which is going to be now a defined type, and I'm going to call that type student data. And if you add that typedef keyword, then when it comes time to actually do stuff with your student data, you don't need to have the struct key. In fact, you can't have the struct keyword there again now. because this student data is now defined as everything between the word typedef and student data is now what I mean when I'm referring to something as student data. Is this better? Is this worse than the other approach? It's different. It's one less kind of keyword. You have to kind of remember it. It's pretty ubiquitous for defining structures in C. So if we want to briefly refactor what this version of the code would look like, the example on the slide did not use a keyword here, but you can still keep it, and you'll see this quite a bit as well. Typedef struct student data. I now need to provide it a name, and I'm going to call that student data T. That's my typedef type here. It's kind of old school. You technically don't need this keyword, but it's still there. By keeping that keyword there, none of my old code is wrong because struct student data is still a defined type. But now I can just replace it throughout with student data T. Or I can just do it for one example just to show that it still works. Because those two types are going to be equivalent. And that is better than doing pound define. Pound define is literally like a copy paste or a cut and paste in your code throughout. This is telling the compiler this is a type that you're expected to be able to handle, and things like, it sounds minor maybe to you, but things like syntax highlighting are a nice feature of it. I've defined this as a type. The compiler should be able to give me good warnings if I'm using the type incorrectly, if I'm trying to assign between incompatible types, and it shows that it's blue, so that's a defined type that I know is valid. When I spell it wrong, should be able to tell me that. Doesn't know what you mean. It even gives me a suggestion that you meant, did you mean student data underscore T. In terms of where these things get placed in memory, technically the rules are somewhat compiler dependent, but by and large the mental model you want to have should be very similar to the same mental model for arrays. We define an int array of size 100. We've basically declared memory for 100 integers effectively next to each other or back to back in memory. Structures are the same way. Once I've declared a variable of that type student data, it's going to allocate memory for the entire structure. There's some weird rules with regards to padding and whether it adds some empty space in between, but for the most part, that's a valid mental model to have, so that I have student 1, it's going to be of a particular size. Of a size we could actually calculate. So the student data T structure, or student dat, is of size. What operator do we use when we want to know the size of something? Seems unhappy about that. I think because it expects it's an unsigned long. It's fine. It'll work. We should know the answer. Again, padding is a little uncertain because it's an odd number of bytes, and sometimes compilers are going to try to be smart. But roughly, we can estimate it should be that's 64 bytes. Let's ignore that 1 byte for now. Plus 8 more, that's 72. Plus 8 more, that's 80. I would say 81. I haven't tested this. I won't be shocked if it returns 84 for padding reasons. Of size 84 bytes. It doesn't like having that 1 byte just kind of sitting by itself. It makes all the underlying operations quite a bit slower. So that was my prediction. It actually added 3 unused bytes in the middle of that declaration to get it to be a multiple of 4. That's the mental model, and we don't have to worry about padding by and large for now. If you're doing low-level networking stuff where the bytes that are sent along the wire between different computers have to be exactly the right length, then you have to start to worry about that kind of thing. But in general, you should be thinking how, okay, we have this structure, and it's actually declaring that much memory at one given time. And then for that reason, and again, that variable can now be essentially used as any other variable is used in our program. We have this concept of we can now have arrays of structures in our code. There's a lot of new verbiage happening today. We already have structures with arrays or structures of arrays. This is a structure, inside it is an array. That's what structures of arrays mean. I've created a structure, inside it is a bunch of arrays. There's advantages of doing that even if only thing inside the structure is an array. We also then can have the syntax for an array of structures. Now that I want to have 50 students or 5 million students in my class, heaven forbid, I just declare an array of that student data type of whatever size I need it to be. And all the other rules that apply for arrays apply for arrays of structures. And we can go quite a bit down a rabbit hole with regards to how much structure and arrays along the way we want to have. The only thing you have to remember, and I think as you start to type it out, it'll be obvious it's the only way that could possibly work, is you now have these two kind of complementary operators. We have the array subscript operator. Give me the ith element of this array. And then we also have the component of a structure operator, the dot operator. Give me this element inside that variable of that structured type. And if we have an array of structures, now we have both. So if I've declared student data and an array of 50 students, and I want to know the first name of the student I would first use the index operator, the square brackets, to give me my students of I. Just like with any of our arrays. Array name of I gives me the ith offset from 0 of that variable of that particular type. My students of I effectively gives you a single student, and then all the rules for that structure then apply. I have a single student. After I've done this part, I now want the dot first name to print it out. In this case, I'm printing out the jth letter, but that's just trying to be difficult because this itself is now an array. So I want to maybe access the jth element of that particular array. I can then do that because first name is a car array. All the rules that apply for a car array are now valid when I access that variable, that component of that particular type. These data types, how you structure them together, those decisions are not made in a vacuum, right? We care about the names of our functions and how we structure our functions, as we've talked about. We care about how we structure our data now for the same exact reason. So having all sorts of combinations of arrays within structs, and then arrays of those structs, and then potentially arrays of structures is all perfectly valid, and the syntax is at least fair, I would say. You know, it's going to get ugly, but it's at least fair in terms of the syntax that one follows for accessing those individual components of a structure inside an array, inside a structure, inside an array, inside a structure. It's just got to be whatever makes sense for your particular program. And we can, I think, pretty quickly come up with a scenario in which, you know, we've defined this student array. But what are students? Students are part of a class, right? And we may want to have multiple classes, right? So something like this is totally valid. We have to make sure we've defined student data before we've defined class data, but otherwise this syntax is perfectly valid. We've already defined our student. We realize that students are part of a class. Well, what else is part of a class? I may need to know the name of the class. I then may also, because it's going to be an array of those students, need to know maybe this is the maximum size, but this is the actual current student count of my students in a class. So I have a structure that has arrays inside it. I have an array of those structures, and then now I'm using an array of those structures inside another structure. Class is just part of a multitude of classes that are being offered within a department. So once I've defined this class data structure, I could very easily imagine, well, I have 25 classes in the department going on at one given time. I would then have an array as part of a separate structure called department, which maybe I have in a name and I have like a class count inside that. Maybe I have multiple departments inside a university, multiple universities inside a state. I mean, you know, it's not just an academic exercise. The data you structure has to make sense for the problem you're trying to solve, for the program you're interested in. But ultimately, that syntax, in which if it's an array and I want the ith element, I use variable name of I. And then once I have an individual structure, I use the dot operator to grab an individual component, of that particular structure. As much of that as you need to do is going to be valid syntactically. This will be our last thing today here. So if I had an array of departments, how would we access the third letter, this is awful, that's why we have a few minutes, of the first name of the 12th student in the 5th department's 4th class? And when I say 12th student, you could say student of 12, whether that's the 12th or 13th student. Let's not worry about that. So student of 12. How would we go about doing that? What would that look like syntactically? I'll do it within this example, although we don't have those other structures defined. How would, and by access I mean like, how would we update? Or how would we read? Third letter of the first name, but name is not an array, but the first name of the 12th student of the 5th department's 4th class. You could work left to right or right to left. It doesn't really matter because it's going to give you the same result. And the way this is worded, of course, part of our challenge as programmers is translation, right? Translating from English to specification, or English to code, or vice versa, from code back to English. So part of this, it's almost like an SAT type question of like, okay, well, what do we mean by this? And it's not exactly in the right order. We have to kind of reorder those sub-statements into a final conclusive statement. I think probably working from right to left would be easier for this example, but it's hard to say. I don't know. How do we access the third letter of the first name? What would that look like in general?
First name.
And for now, I'd say dot first name of 3. Whether that's the third or fourth letter, let's not worry about that. The problem isn't that important. This is going to be working from right to left then. That is, once I have an individual student, there's a first name component, and that happens to be an array, I want the third letter. Somebody else now, what's the next one we would have to do? Yeah, and we didn't really define an array yet. Students, I guess. Well, let's be clear here. I guess in this example we did. My students is what we called it when it's within an individual class. My students of 12. My students of 12 is an array. None of this is going to compile, right? We didn't define all these classes in the program. But syntactically, it's correct. We just don't have the other stuff here. My students of 12 is part of this structured definition. So that also requires a dot operator. What's next? So that's students of 12. It's part of the class data, which is part of that array, my classes, of 4, the 4th class, which is an array. So we use the array syntax to grab the 4th element or the 4th offset, whatever, of that array of my classes. But that is also, it's both an array, it's also part of a structure, it's part of a departmental data structure, of which there's an array of departments. We don't define that variable, but it's either defined as an array or it's part of some other structure. The problem doesn't really say of the 5th department's 4th class. That's going to be one big, compiler error, so I'm just going to comment it out because none of that stuff is defined. This syntax looks like it's unfair almost, right? That, hey, why are we accessing this? And so we could have gone from left to right. Hey, I need the 5th department. Okay, my department's of 5. I need a certain class inside that department. That's my department's dot my classes, and I need to figure out which one I want. I now have a class. I need to grab a student from that class. From a student, I need to grab their first name. And just to make it difficult, from the first name, I need to grab a particular character of that individual array. Yeah, and I said, let's not sweat it. Yeah, technically, this was already an annoying enough question. The third letter would be this. This is the third offset. Okay. Maybe we're just skipping the null student in every class because that could lead to problems. There was a student last year whose name was broken in the system and it showed up as null in Canvas. Caused all sorts of problems with Canvas. We haven't talked about null pointers yet. It caused all sorts of Canvas problems all semester long, and you'd think they would have thought that through. This poor guy was named Null. This looks unfair. This looks like a fake example. This isn't that far off from what your Lab 7 code is going to kind of look like at the end of the day. Our code is always going to have structure. And I would argue, well, this is quite lengthy now. This is accessing a single car. This is better than the alternative of just trying to manage a whole bunch of different named arrays in trying to remember what was the name of the array for that class corresponding to this department corresponding to that student. Here, it's lengthy, it's wordy, it's at least kind of fair, logical, and consistent in terms of how we access that particular member. And of course, we don't access 5, 4, 12, 3. We access I, J, K, I guess L at that point, because we're going to be doing it as part of some loop where we're going to be accessing it. That's what we'll do in Friday's example in class. We'll build an array of students, and we'll show that ultimately you have to keep track of this, but it'll look otherwise like the code we've already been doing all semester.